Hi, today we're going to investigate how your calculator can help you find the best fitting line for a given data set. Our calculators, the TIs and most, use the method of least squares, it's called. So they call it the least squares regression line to find that equation. Two characteristics of the least squares regression line are these two. It contains the centroid of the data set, so that's something we're going to have to find out about a little bit. And it minimizes squared error. Minimizes squared error. And that's all in an attempt to get that line as close to as many points as possible, because that's what makes a good best fit line. We're going to use this tiny data set to look at this. I'd like to have you make a scatter plot of it out in your corner. X's are 1, 2, and 3, so I'm going to just say starting at 0, 1, 2, and 3. The Y's go from 0 up to 5, so 1, 2, 3, 4, and 5. As you plot these points, again, very small data set, first point at 1, 0, then 2, 4, and then 3, 5. So you can see that the trend is increasing here. Let's talk about that centroid. The centroid of a data set is the point that is the average of the x values, comma, the average of the y values. You can think of it as the balance point of a scatter plot. Average x for us, well, we have 1, 2, and 3. That's a total of 6 divided by 3 items. So the x average is 2, the y average. The y's add up to 9, and there are 3 of them. So the centroid of our data set is the point 2, comma 3. So any best fit line, any least squares regression equation will have to contain that centroid. I have on the next page 4 possible candidates for that best fit line, and you can see that their equations are under them. All of them are relatively close to points on the line. Some look like better choices than others, and our job in this lesson is going to be to decide which one the calculator says is the best fit line. One of these does not contain the centroid. So let's put a 2 in for x and evaluate the y. If you do not get 3, that's the one that doesn't fit. So we know that y equals x plus 1.5 is not a good candidate. If you put 2 in for x and all of the rest, y would equal 3. So the centroid, these are all still in the works. 2.5 times 2 is 5, and 5 minus 2 is 3. 2 times 2, 4 minus 1 is 3. So all 3 of these contain that centroid. That second criteria for the least squares line is that the sum of squared error be as small as possible. Sum of squared error. And I'd like us to take a look at each of the remaining lines that could be our best fit line and look at the sum of squared error. I'll show you what I intend to do. We've got the actual data set sitting here, so this is the actual y. We're going to predict a y using the equation that's shown to the left. So for this one it would be y equals x plus 1. What we're going to do to find the amount of error, always subtracting in this order, actual y minus predicted y. Then we are going to square and sum that error. I'm going to do that for these 2 lines. I'm going to ask you to do the same thing. You can see my work here. In the first line, I predicted values of y by inserting the x that was given into the equation. I subtracted and squared, and I did the same thing for this line. Of the 2 that are showing here, this one is by far the better choice, but we have one more to do. Here's its equation. I'm going to ask you to pause that video and find the sum of squared error for this particular line. Here's my work for that. While this is close, its sum of squared error is 2. That means that our candidate 2.5x minus 2 would be the line of best fit according to the calculator, the least squares regression line. And as you look at that, you can tell it is a very good fit. It hits 2 of the points, and it's very close to the third. Okay, this is a much better choice than any of the other two, both visually and by using the criteria. Contains the centroid and has the smallest sum of squared error. I'm asking you here to test the result, what you said or what I said, by using the calculator's lin-reg functions to find the equation that it says is the best fit. So I'm going to get my calculator up, I'll go through the keystrokes, and then we'll try it. I have my calculator up, and I have put the x values in list 1, the y values in list 2. To find the equation of the least squares regression line, you have to have your data again in list 1 and 2. Then it is stat over to calc. Let me write that here. Stat, arrow over to calc, and we're going to choose lin-reg. See it right there, number 4, linear regression, and it will give us in the form slope times x plus b intercept. So it's stat, calc, and then lin-reg. My calculator is giving me options of where I want to have my x's and y's. I have them in list 1 and list 2. The frequency list should be blank as far as I know. You can have the calculator store the regression equation. I'm not going to do that. I'm just going to ask it to calculate. And here's what it says. That y would equal 2.5x minus 2. Fancy that. That's exactly what we said. To paste that into the y equals, if we wanted to look at the line with the scatter plot, which is a good idea, what you do is go to your y equals, clear if necessary, so I'm going to do that. Y equals, I don't have anything in there. With my cursor still here, I'm going to follow these keystrokes. It's the VARS key, V-A-R-S, VARS, option 5 for statistics. Then it is arrow over twice to EQ, and choose Reg EQ. Notice how that put the equation right here. Now I want to see that with the scatter plot. I'm going to make sure that I have my settings correct. Here are the settings that will show me the scatter plot. I'm in plot 1, so that was stat and or second and y equals to get here. I have scatter plot turned on. It's looking at lists 1 and 2. I can set the window that I had in my previous graph, or I could ask the calculator to do a zoom fit, but I had an x going from 0 to 4. We had to get past 3, as I recall. Y's went from 0 to 6. Again, we had to get higher than 5. And I'm going to go ahead and hit graph now. And there's the scatter plot with the regression line. See, very nice. That lin-reg is a wonderful tool. I'm going to ask you to use it one more time. I have an example problem here about earthquakes. So, well, our x is the magnitude of the earthquake on the Richter scale, and y is the depth in kilometers under the Earth's surface where the epicenter was. So what this says is to use the calculator to create the plot, find the equation of the least squares regression line, put it with your plot, and then use the equation to predict the depth below the surface if that quake measures 3.7 on the Richter scale. Alright, ask you to stat and enter. Have you put the x's in list 1, the y's in list 2, and then carry on. So pause the video and let's try that. Here's the scatter plot that I came up with. It does look kind of scattered, but I can envision a line that would go through the middle. Let's come on and get that line. If you'll recall, the keystrokes to find the linear regression are stat, over to calc, choose number 4, lin-reg, As long as your stuff's in list 1 and 2, you should just be able to go to calculate. And here's the equation that the calculator gives me. Y is approximately equal, I'm going to round to the hundredths place here, 2.16 x plus 0.22. To paste that into the y equals so that we can see it with the plot, clear out that y equals, it's vars, number 5 for statistics, over, and choose reg EQ. That puts it into your y equals, so when you hit the graph key again, by the way, I used a zoom stat window, that's a zoom 9 window. Here comes my line, and there it goes. Right? Divides the points pretty evenly above and below, hits a couple of points right on, so not a bad line. We're asked lastly to predict based on this equation. So if we have a Richter scale measurement of 3.7, that's an x value, what we're going to do is substitute that in, 2.16 times 3.7, add 0.22. I came up with a depth of about 8.2 kilometers below the surface for that epicenter. Very good. That's it for today. We're going to ask you to get out there, try the U-Try, and we'll see you in school.